Okay, let's take a look at one more example of a circuit problem involving Thevenin's theorem in which we have no dependent sources. So we'll just review our procedure here. We're going to treat the load as open, calculate our R Thevenin using these rules. Then we'll use superposition and solve for the Thevenin voltage and then solve for the unknown. Okay, so let's start by solving for the Thevenin resistance. Solve for the Thevenin resistance, we treat all sources as if they were open. Now, there's one exception to that in this case. This voltage source is actually what we're considering to be the load. And so we always treat the load on the circuit as if it were open. Okay? So where we would normally think of a voltage as being shorted, here it's going to be open. Okay, so that's what our circuit looks like with all of the sources removed. And again, remember that we're calculating the resistance across our open terminals here. So when you look at this, you'll see that the 5 ohm resistor here at the top contributes nothing, and that the rest of the resistors are in series. And so our Thevenin is simply 35 ohms. Okay, next let's solve for our Thevenin voltage. We'll do that by looking at each source as if it were acting alone in the circuit. So we'll start with our source 1 up here. Okay, and now it's important to remember that we need to be concerned about the polarity, and this is something that we haven't run into before, where we had a voltage source in here instead. So maybe there's a little bit of a question as to what that polarity is supposed to be. And what we want to do is just go ahead and use the polarity assigned by the battery. Okay, so even though typically we would think of this as being a load on the circuit, it's actually going to be providing power to the circuit. Okay, so we'll use the polarity of the battery just like that. And that's what we're going to call V prime on the open circuit. Okay, now let's notice that this whole entire branch down here, not connected to anything, isn't contributing at all to the voltage in the circuit. So we could take this negative terminal of V prime and bring it all the way back down to here, and that's the same thing. Okay, so if we could just calculate the voltage across these two resistors, then we're cooking with gas. So let's make sure that they're also that we understand what their polarity is, and by the resistor or the current source here, you'll find that we have the same polarity with V prime on the open circuit as we do with the voltage across the resistors. Okay, so V prime is going to equal 4 times 10 and 4 times 5. So V prime equals 60 volts. Okay, let's look at the next source. So for that source, let's see, we remove the other one. And so it looks something like this. Again, we have that dead branch up here that's not going to be contributing anything to the circuit. So we'll be able to ignore that. And we're going to call this V double prime. Okay, so this doesn't do anything. And now we want to find this voltage. Well, stare at the circuit for a little bit and see if there's a way to minimize it. Well, this isn't doing anything. This wire sticking out here. So the negative terminal comes all the way back here. And what's the voltage from the 10 ohm resistor? It's got to be 0, right? There's no current flowing through here. Can't be, because you can't have current without a loop. So we could think of V double prime as simply being the voltage across this source here, which is 2 amps. Okay, well, I don't know what the voltage across the source is, but I also can calculate that voltage by looking at, by traveling around here like this, right? Voltage between here and here. And I know that because the current can't be flowing into this right branch at all, that all of it flows in here. So again, we'll look at make sure that we've got our polarity right. And you see that the polarity of this current tells us that the voltage is going to be the same direction as the voltage V double prime. So V double prime then equals 2 times 5 plus 2 times 20. Okay, which equals 50. So now let's combine our results and remember that V on the open circuit is equal to V Thevenin, and that these are equal to the sum of the contributions of both sources. Okay, and that equals simply 110 volts. Okay, so now we have our Thevenin equivalent and we have our Thevenin voltage. So let's draw our Thevenin circuit. Okay, and both of these, my other example didn't show this, but if you get these negative, well, you're not going to get negative resistance, hopefully, if you do the math right. But if you get a negative voltage, you just want to flip the polarity of from your standard Thevenin voltage. But we didn't get that in this case. So let's draw this. And what is it we're putting in here? We're putting a 40-volt voltage source and we're looking for IA. So what I'm going to do, just to simplify this here, oops, and this is 35, is I'll combine these two resistors. So that's going to be 110 minus, oops, what was that number again? 40. Okay, minus 40. And so that'll be 70. Okay, so it'll look like this. And you'll get that if you just do KVL around the loop, right? 35, and we're looking for this, IA. Well, just by this battery here, this voltage source, I can tell that the current flowing through this circuit has got to be in this direction. So IA is going to be negative of whatever value we get. And I let's call this I, negative IA equals I, which equals 70 divided by 35, which equals 2 milliamps. Or, oops, 2 amps, right? 2 amps. And so IA is equal to negative 2 amps. And that's the solution to that problem.